Okay, welcome. Good morning to Chapter 7 for the limited X-ray machine operator. We're going to cover the principles of exposure and image quality. All right, so these are our learning objectives for this particular session. We're going to learn prime factors of exposures. We're going to talk about formulas specific to determining milliamperes per second and explain how the unit is useful to us. Explain the radiographic defect of the four prime factors of exposure, also the radiographic distortion, and explain the difference between magnification and shape distortion. We'll recognize the changes in radiographic density and state the exposure factors used to control density, identify high, low, and optimum contrast on a radiograph, and state the exposure factor that primarily controls radiographic contrast. Define spatial resolution. We're going to list and explain geometric factors that affect the recorded detail of the radiograph images and explain why magnification affects the detail. And we're also going to list and discuss the methods for minimizing motion blur on radiographs. All right, so here's the prime radiographic exposure factors. Milliamperage, MA, controls radiographic density and controls quantity of the X-rays produced. It is controlled by adjusting the MA, and the quality of the exposure is directly proportional to MA. The exposure time is represented in seconds, otherwise MAS. That's actual exposure time of milliamperage, but exposure time is time in seconds, represented by S. It also controls the radiographic density. It controls the quality of the X-rays produced and is controlled by adjusting the timer in the X-ray circuit. It also controls the duration of the exposure, and the quantity of exposure is directly proportional to exposure time. Now, kilovoltage or kVp, it controls radiographic contrast. Okay, contrast. This is the X-ray penetration. The quantity and the quality of the X-ray beam is also affected, and the increase in kVp results in an increase of quantity of photons and that penetrate the body part itself. So source image receptor, we've beaten that one up quite a bit, the SID. It affects the density and the intensity of the X-ray beam. It is that distance between the tube and the image receptor. The quality or the quantity of the exposure is inversely proportional to the square of the distance. All right, some prime radiological exposure factors as we continue. Let's talk about milliamperage. It affects the exposure rate, volume, or number of X-ray photons produced per second. Exposure time, it controls how long the exposure lasts, and the exposure is directly proportional to the exposure time. Milliamp seconds, or MAS, it indicates the total numbers of X-rays in an exposure. The exposure and the patient dose are directly proportional to MAS. MA is times time equals MAS. You can see this formula represented on the bottom. If we have 200 MAs, that's 200 milliamps, and we expose the patient at a level of 0.05 seconds, that's in the automated control section, that's going to equal 10 MAs, 10 milliamps per second. So pretty easy math there, folks. But that is your formula. That is the primary controlling factor of density. All right, so kilovoltage, we talked about penetration, okay? Kilovoltage controls the wavelength and the energy of the X-ray beam. It specifically controls the power and the speed of the electrons within the tube current. The energy is related to the ability of the X-rays to penetrate the patient and reach the image receptor, or the IR. So primarily controlling factor of penetration and contrast is the kilovoltage. Increasing or decreasing kVp, what it does, it decreases the wavelength, energy, and penetration of the X-ray beam respectively, but not in direct proportion. All right, so in the source image receptor distance, the SID, this is where the X-rays diverge or spread as they exit the tube. The amount of divergence depends on the length of the SID and the effects of the intensity of the X-ray beam. As you can see here in this representation, this diagram here, the common SID or D1, distance 1, is 40, okay? And then the total D2 distance, that is to the IR itself, let's open this, or the radiation field itself, is 80. All right, so understanding that the inverse square law states that radiation intensity is inversely proportional to the square of the distance is a hallmark towards understanding the clarity of X-ray images. So this is your formula here. You have I1 over I2 equals D2 over D1 squared. You can see that the I1 represents the original density, I2 is the new density, and D1 and D2 is the original SID and the new SID. Density or overall blackness of the radiograph affects visibility of the image detail, and it is primarily controlled by the MAs, although KVP, SID also influences density. An image is lower density, the A image on your left here is in lower density, and the B to your right is in a higher density. Now, obviously in your higher density, it's much easier to read, as you can see here represented on these two radiographs. All right, so the contrast or difference in density between adjacent areas of an image, it creates the visibility of detail, and it is affected by the KVP and that is the primary controller. The subject contrast is the variation in beam intensity after it passes through the patient, and the radiographic contrast is the combination of the IR and the subject contrast. With contrast, the optimal contrast may be high or low depending on the composition of the body part. Low contrast is less difference between densities, okay? High contrast is greater difference between the densities. Okay, the size distortion or magnification is where the atomic parts or the anatomic part appears to be larger than it actually is. It is affected by the SID, which is the source image receptor distance, and the OID, which is the object image receptor distance. This is very clear on figure 7-8 on page 83. All right, so shape and distortion or unequal magnification. It can be varied by the length or shape of the anatomy and is misrepresented or may be caused when the body part is not parallel to the IR or the image receptor, or when the CR, the central ray, is angled. So these diagrams, you can see the representation of the item is the distance, and then the actual CR, and then, the beam of the CR, and it shows you where the beam is coming in as an angle, and it can create these kind of distortions. All right, so spatial resolution, it refers to the image clarity, which is affected by motion. We call this either a quantum model, which is a grainy, spotty type of image. Then also the focal spot, or the small or large size, the OID, which is the object image receptor distance, and of course the SID, source image distance. It also is referred to as resolution, sharpness, definition, or detail. So let's discuss that in a little bit of detail here, each one of these. All right, so specifically the umbra is the actual body part of the penumbra and describes the unsharp edges of the umbra. And then the factors that create these problems are between SID, OID, and also focal spot size, either small or large. So, if you're not doing it correctly, then you're going to get these types of image differences. All right, so as you can see in this diagram, the focal spot is shown. The small focal spots produce less penumbra. This results in a very sharper image. Okay, so you can see this here. Let's get rid of me. All right, so your penumbra, you can see the penumbra here. These are your edges. This is the edges of your IR, edges of your image. Okay, notice that the penumbra is here. All right, so we have a small focal spot. The penumbras are small. You have large focal spots, your penumbras are quite a bit bigger here and here. All right, so the biggest thing is we want to focus on getting our collimation to make a very smaller focal spot to be able to get a good representation. All right, so the OID and SID, let's talk about that real quick. OID is the object image distance or receptor distance. By reducing the distance between the object and the IR, we're going to decrease the penumbra and the OID. The SID, which is the source image, if we increase the distance between the radiation source and the IR itself, it decreases penumbra. So we want to use the longest OID and the shortest OID and the longest SID that's possible. Okay, absolutely, that'll give us the best image. All right, so motion, patient motion is a big factor in getting a great exposure. It must be limited. Movement of the patient, the image receptor and X-ray tube will cause blurring. It can be voluntary of the patient or involuntary. If the patient has pain, patient has, spasm of a particular appendage that you're trying to X-ray. So effective communication is a key factor in avoiding the motion in the image itself. The principal means of controlling that motion is to use short exposure time. So therefore, you're not putting the patient through, a whole lot of, waiting for an X-ray and waiting for the exposure to happen. So in summary on this particular chapter, the prime exposure factors are milliamperage, exposure time, MAs, and SID. You need to make sure you got this down pat because you'll see those on the test. The prime exposure factors that are manipulated to control the radiographic quality factors, you know this, is density, contrast, and distortion. Spatial resolution refers to image clarity. Make sure you know that one. And penumbra is the inherent blurriness in the radiographic image. You will definitely see that on the test. And we can reduce the penumbra and the image sharpness by increasing the appropriate SID and OID as well as the focal spot size. We also need to pay attention to image sharpness. It can be affected by motion, intensifying the screen speed, and also film screen contact. So we need good communication with our patients when we're doing our x-rays, and there'll be less movement, reduce the time of the seconds of exposure, because the more time the exposure, the less, the higher the ability the patient's going to move during that exposure time. Okay. Any questions? You can go ahead and email us at student@emets.net if you're an EMETS student, or if you're an EMETSCI student, you can email us at student@emetsciinstitute.com. Thanks for your attention on this chapter, and we'll see you next time.